Hi everyone, we're going to get started on chapter 5 dealing with stereochemistry. So stereochemistry is what you guys will really be dealing with when you're working on the lab this week also. So stereochemistry is the study of the 3D structure of molecules. So previously we looked at two different types of isomers. So we talked about constitutional isomers. So constitutional isomers differ in the way that they connect, so how atoms connect to each other. We also have something that we talked about really briefly, so we have stereoisomers. So again, stereoisomers are going to be the main talk of today. So stereoisomers, they have the same bonding or connectivity, but they differ in the way they orient in space. So if you think about it, an example that we have talked about when we think about chair conformations, we looked at cis and trans conformations. So if we look at this molecule here, we would think, okay, this is going to be a cis conformation. If we look at this molecule here, this would be our trans conformation. So again, these are going to be stereoisomers because this substituent here, this methyl group here is different in how it's going to orient in space. So a new thing that we haven't really talked about yet, stereocenter. So a stereocenter, it's usually depicted with this asterisk. So this is going to be an sp3 carbon atom with 4 different substituents attached to it. So an example of this would be this molecule here. And just a reminder, remember that this is pointing towards you and the dash is pointing away from you. So if we look at this carbon atom right here, we have 4 different substituents attached to it. So this carbon here would have a stereocenter. So another topic that we are going to talk about is going to be chirality. So there's a lot of definitions in the beginning, but then we'll kind of apply everything towards the end of this chapter. So any object or really molecule is considered to be chiral if it has a non-superimposable mirror image. So what a non-superimposable mirror image really means is it means that it's not identical. So an example of this would be your left hand versus your right hand. So your left hand and right hand are going to be chiral, which means again that they are non-superimposable mirror images, which again means that they are not identical. So non-superimposable mirror images are also called enantiomers, and we will discuss this in a little bit in more detail. So again, chirality is just telling us that we have 2 molecules or objects that have non-superimposable mirror images. If we talk about an achiral molecule, so an achiral molecule, what this is going to be, it's going to have identical mirror images. So let's look at some examples of both chiral molecules and achiral molecules. So example of a chiral molecule. So again, think chiral molecule, it means that we have non-superimposable mirror image. So if we draw our molecule like this, We look at this carbon. This carbon is going to be, again, have a stereocenter because we have 4 different types of substituents that are attached to it. If we look at its mirror image, so imagine a mirror plane. And when we draw the mirror image of this, it's going to look like this. So what you'll want to do is you're going to take this molecule here, and we can rotate this 180 degrees. So we'll rotate it here 180 degrees. So when we rotate this 180 degrees, what we see is a molecule that looks like this. So we'll call this molecule A, we'll call this molecule B, and this molecule will be B rotated. So let's look at some differences between A and B rotated. So these are going to be considered non-superimposable. So they're non-superimposable because they are, again, not identical. So if we look at it closely, Cl has a wedge in A, and Cl has a dash in B rotated. So again, remember that stereoisomers are different in the way that they orient in space. So what we can say is that A and B have different orientations in space. So again, they're mirror images, but not superimposable. A is a chiral molecule, and we would call B its enantiomer. So let's look at some examples of achiral molecules. So again, think achiral molecules. It's going to mean that their mirror image is going to be identical. So if we look at this molecule right here, we have, looking at that carbon, we'll notice that this carbon right here is not a stereocenter, right? Because we don't have 4 different substituents that are attached to that carbon. So if we look at the mirror image of this molecule here, and then we can rotate this 180 degrees. So when we rotate it, we can rotate it right here, 180 degrees. So the reason that you rotate it really is just so you can kind of compare so right here we have both hydrogens as either the wedge and dash. So that's really the idea behind, behind the rotation. So when we rotate this 100 degrees, we can see that this structure here and this structure here are identical. So if a compound has no asymmetric carbon atom, so if it's not a stereocenter, it is usually achiral. So let's look at a few more examples of achiral molecules. So if we look at, so we'll call this one B. If we look at this molecule here, so we have ethylene. So this is going to be a planar molecule, right? Because we have sp2 hybridization. So if we look at this, we have a mirror plane in this direction, and we have also a mirror plane in this direction. So considering that we have those 2 mirror planes, we have the same types of substituents attached to both of these carbons, we would consider this also an achiral molecule. Another example is, let's look at this molecule here. Sorry, my benzene rings or my aromatic rings aren't great. So if we look at this carbon right here, so carbon is or has a stereocenter, right? So if we look here, we have a mirror plane, an internal mirror plane here, which again, what this really means is that the left side of this molecule right here is the same as the right side of this molecule. So with that internal mirror plane, that would make this an achiral molecule. We also can look at an example like this. So same exact idea. So the top half of this molecule is going to be exactly the same as the bottom half of this molecule. So we would consider this an achiral molecule. So let's look at conformation and chirality. So molecules that can achieve a specific conformation with an internal mirror plane are going to be achiral. So again, achiral means that they are going to be, their mirror images are going to be identical. So this can happen even if the molecules have a chiral center or stereocenter. So let's look at a few different examples. So if we look at, let's look at this first example here. So this molecule here. So let's imagine our mirror plane. So when we look at both of these, we can see that their orientation in space is not going to be exactly the same. So these are actually going to be non-superimposable mirror images. So these would be considered chiral conformations. Let's look at this molecule here. So looking at this molecule here, we can see that both carbons are not going to be considered a chiral center or a stereocenter. We have this internal mirror plane here. So again, this left side of the molecule is exactly the same as the right side of the molecule. So since we have this internal mirror plane, this would be an achiral conformation. So we have different types of classification of stereoisomers. So this is going to start where lab's going to kind of come into play. So with some of the definitions and things that you guys will be covering. So we have two major types of stereoisomers. So we have enantiomers, which we've talked about a little bit. So enantiomers are going to be those non-superimposable mirror images. So there's a few examples above, but we'll also look at a few examples in a little bit. We also have diastereomers. So these are going to be stereoisomers that are not mirror images. So what's going to be really, really important for our lab this week is their physical properties. So when we look at enantiomers, these are going to have the same physical properties. We'll have a lecture on this a little bit later in the week. And then diastereomers are going to have different physical properties. So let's look at a few more examples of enantiomers. So if we look at this molecule here, let's think of its mirror image. So our mirror image would look like this here. So if we rotate this 180 degrees, we are going to have a molecule that looks like this. So comparing this molecule to this molecule, we can see that the stereochemistry of these groups here is different. So these are not identical. They're non-superimposable mirror images. They are different in the way that they orient in space. So we would consider these enantiomers. And then remember, enantiomers, it's important when you have a group of enantiomers that you know that they have the same type of physical properties. So if we look at this molecule here, so you have your axial and your equatorial, you can kind of think cis and trans, that may help you. So if you look at your, sorry about that. So if you look at your mirror plane, what we're going to have is this molecule here. So this would be considered trans, right? This would be considered trans. So these are both enantiomers because, again, they're different in the way that they orient in space. Think of, again, axial and equatorial positions. So again, these type 2 compounds would have the same type of physical properties. So let's look at some examples of diastereomers. So again, diastereomers, remember, they are stereoisomers that are not mirror images. So if we look at this molecule here, versus this molecule here. So here we would have a trans cyclobutane ring. Here we have a cis cyclobutane ring. So they have the same connectivity, but they have a different 3D orientation. So these are not mirror images, so we would consider these diastereomers. So again, remember, diastereomers are going to have different types of physical properties. Another example that we can look at would be this molecule here versus this molecule here. Sorry, this should be a single bond. So we have trans and cis. So again, these would be considered trans and cis isomers, or we talked about geometric isomers. That all means the same thing. So these would be examples of diastereomers. Again, they're different in the way that they orient in space. So diastereomers, again, are going to have different physical properties. So this lecture is going to end right here, and then we are going to pick up with the CIP rules. So I will load a lecture talking about that within the next couple days. All right, have a great day, guys. Bye.